All right, I'll introduce Artan Sheshmani, who will speak today about global shifted potentials for moduli stack of sheaves over Calabi-Yau fourfold.
Thank you very much. Thanks for inviting me to this amazing conference. And sorry that I couldn't be there in person. And however, I've been enjoying the talks. So this talk has a little bit of flavor of derived geometry in it. And I was actually thinking how I should start kind of motivating it. So I thought maybe I should just make two examples of sheaf theory on Calabi-Yau 3 and Calabi-Yau fourfolds, compare them together so that you can see some pattern there, and then hopefully that motivates the construction. So, okay, so let's start. So to motivate the construction, consider sheaf moduli spaces over the following Calabi-Yau 3 and Calabi-Yau 4 examples. I'm gonna draw a comparison between them. So here's the first example. Let us assume that I have a Calabi-Yau 3 and which is a K3 fibered threefold. So it's think about some pencil, let's say pencil of cortex, for instance, over P1 or any curve. So this is a Calabi-Yau left chest pencil of cortex over P1. This is a Calabi-Yau threefold. We are interested in considering sheaves, coherent sheaves on this Calabi-Yau threefold, K3 fiber threefold, with support. So sheaves are going to be supported on fibers of this Calabi-Yau 3. So let's call them X3 pi. So sheaves are supported on finitely many fibers of this Calabi-Yau 3. Okay. So let us denote the moduli space M of F, the moduli space of Gieseker stable sheaves. These are torsion sheaves. As you can see, they are not supported on all of X. They are supported on fibers of X over P1. Gieseker stable torsion sheaves on X3, and the Chern character of F should tell you where they are supported. So their rank is 0 because they are torsion. Their first Chern class is the Chern character is telling you their rank as well as their support. So R times class of F. Let us define F as the fiber of Calabi-Yau 3. So they have some second Chern class, curve class, and some third Chern character associated. Okay, so Gieseker stability is as usual. This thing sits inside P1 times P3, and it's a quasi polarization and can pull back the line bundle from ambient projected spaces, and that defines for you a notion of polarization for your stability. Okay, so that's the setup. Now we would like to define some notion of invariant on this moduli space, some notion of enumerative invariant over this moduli space. Let us assume that this moduli space is a smooth manifold, for instance. Let's say assume it's not, but let us assume it is. If it's a smooth manifold, then one of the invariants is Euler characteristic. So I can define Euler characteristic of the moduli space, and that's an enumerative invariant. It's a deformation invariant. If you deform the underlying threefold X3, invariant doesn't change. It's actually even a topological invariant. It's much stronger than a deformation invariant. And based on differential topology, so differential topology actually tells you if you have a manifold, you would like to calculate this Euler characteristic, it's basically a inner product between homology and cohomology classes associated to that manifold. So what you do, you integrate over the fundamental cycle of your manifold, the top Chern class of its tangent bundle with a sign. So that gives you Euler characteristic. The problem issue in here is that the issue is that M is not smooth. So algebraic geometers come up with modifications of this thing, which I'm sure by now, in the middle of the week, you have seen talks about Gromov-Witten invariance and other types of invariance. So you already, I think everyone in the audience at least knows. So you can define rather virtual Euler characteristic of the moduli space. So that's a modification of the previous one. So you would be replacing the fundamental cycle of your moduli space with some artificially designed class that represents the moduli space in expected dimension. And if you're lucky, you can, moduli space not being the smooth, it implies that the tangent sheaf is not going to be a bundle and it has higher obstructions. So you would need to find some suitable bundle that parameterizes those obstructions, and that's the obstruction bundle. And it's not that you can always find such obstruction bundle. Sometimes you have obstructions to obstructions. So the obstruction sheaf will not be a bundle, and that's problematic. Okay, so you can define this notion of virtual Euler characteristic, and basically this is what is the Donaldson-Thomas invariant. So all of it was defined and computed in many examples by Richard Thomas himself and many of his students and collaborators. Okay, so this would be an invariant of deformation of the scalar and complex structure of the underlying X3, the Calabi-Yau 3. You can also show, we can show something about the structure of this moduli space. We can also show that, in this case, there exists a Chern-Simons type potential function such that the moduli space is given by moduli space of sheaves, as I define, is given by critical locus of that potential function. So let's call the potential function phi, critical locus of phi. And if you can find such potential function, there's other way of calculating the invariance using the sheaf of vanishing cycles associated to this potential function. Basically, it is the minimum fiber construction. Okay. So let me dig in a little bit more into showing you how nice this moduli space is. I mean, we all know by now that moduli space of sheaves on Calabi-Yau threefold are kind of nice. Invariants are always definable on them. So let me just remind for you how nice they are. And then when we go to fourfold, you will see the problems. So let us study this better. So I have this X3 fibered over P1, and I have the K3 fibers. Our sheaves are supported on the fibers. So this is my, let's say this is my P1. I want to draw pictures every now and then. So our sheaves are supported on the K3 fibers. And over the fiber, I'm going to call them G. So every sheaf, torsion sheaf we are considering in this moduli space comes from the fiber. Okay, so in fact, these sheaves are always push forward of the sheaf G over the fiber, where G is a module over the structure sheaf of the fibration. So these are K3 modules, all K3 modules. Okay. Now, in order to study this problem better, one trick that I really like is to pull back the sheaf. So the sheaves are pushed forward of G's, and you can pull them back, but pulling them back means you can tensor them with the structure sheaf of the fibers. That's something that is not necessarily just the usual tensor product, but it will be a drive tensor product. So if you pull them back, you will get back the original sheaf G, And then you will get some piece that remembers how the fiber sits in the ambient Calabi-Yau threefold. So here N is the normal bundle. N is the normal bundle of the K3 fiber in ambient X3. Okay, so this is an exact triangle in bounded derived category of the fiber of this K3 fibration, and this is due to Bondal and Orlov. They show that this exact triangle always exists for torsion sheaves. Not only that, exact triangle is a split. So in fact, yeah, you can see that this is isomorphic to G plus G shifted by 1. Okay, this is co-normal sheaf now, but it has a shift in the derived category. Okay, so now one thing you can do is you can apply R blank comma G. You will see soon why I'm doing that to this exact triangle. Apply this to the split triangle delta. If you do that, you will just see that it starts from right-hand side, R GG, then R pull back of the push forward of G comma G, R G, tensor the conormal sheaf. I'm gonna put this shift in here outside. So I can put the shift outside, but it becomes a -1 because it's in the contravariant component. Okay, so it becomes something like this. And then, as you can see, there is the left adjointness of the drive pullback and the right drive push forward, which implies that immediately this thing is nothing but basically you can take this part and move it into here. And then you can replace these things with F, because that's by definition our torsion sheaves in the ambient variety. Okay, so when you do that, in the middle you have R F comma F. So in some sense, in some sense, it's like you're ignoring the I lower stars. Now it's an exact triangle. This is an exact triangle in bounded drive category of the moduli space itself. Or, okay, if I'm doing it for one sheaf only, it's an exact triangle, not for family of sheaves, but just for sheaves. It's an exact triangle in bounded drive category of X3. Everything is now back in X3. And this exact triangle, let's call it delta prime. Delta prime is also a split, of course, because delta was a split. So let us just write that down. So let's call this one F dot. I'm gonna call this one G dot, and I'm gonna call this discrepancy in here D dot. If you actually move this N dual to here, it becomes G comma G times N, and it basically tells you, so one way of understanding these things is if you take cohomologies, look at R F comma F. It is parameterizing homomorphisms of F, deformations of F, X1, and obstructions to those things, X2. Same thing goes for G, and this is just some discrepancy term. So in some sense, it actually tells you that deformations of the sheaf, torsion sheaf, which is always realized as pullback of push forward of some sheaf on the fiber, is captured by how the sheaf on the fiber deforms, that is G dot, captures those cohomologies, and that the discrepancy basically tells you contribution of infinitesimal deformations of the fiber to deformations of F. So that's that. Okay, so R FF is isomorphic to G dot plus D dot, discrepancy term. Okay, now let us look at cohomologies of this. As I said, this is FF, X1, X2, it's on a threefold, and X3. Okay, now by Serre duality, actually, these two terms are equal to each other. And if you're looking at the stable terms, stable sheaves, you can actually see that deformations are captured by the trace-free Hom FF and trace-free X3. Hom FF alone is isomorphic to C, and the trace-free is isomorphic to 0. And by Serre duality, this piece also vanishes. So you can actually capture that the complex R Hom F comma F has only non-zero, two non-zero vanishing cohomologies, and this is the most perfect suitable object to calculate invariance. So we say that R Hom F comma F is in some sense, is the tangent complex of the moduli space, which is perfect of amplitude, but this term sits in degree 0 and this term sits in degree 1, perfect of amplitude 0, 1. Dually speaking, this dual of this maps to the cotangent complex of the moduli space, and it's a perfect complex of amplitude -1, 0. It is suitable to design the virtual fundamental class over the moduli space, and the invariance can be calculated. So let us just stop at this point. Okay, so this is the threefold theory. Now to draw the comparison between this and fourfold theory, let me show you. By the way, maybe a remark actually. There was this work of mine with Gholampour in 2018, which as soon as we realized that this has these nice properties, we actually computed the virtual fundamental class of the moduli space with respect to this deformation obstruction complex. And we show that it is basically given by virtual fundamental class of the fiber-wise moduli space. Basically, moduli spaces of the fiber. So moduli space of Sheaves F, its virtual cycle is the moduli is given by moduli space of Sheaves G, the fiber-wise moduli space, and its deformation obstruction complex. Okay, cap with top churn class of H1 of the discrepancy term. And this discrepancy term is this one. Okay, this is a formula, and this formula tells you as you integrate over the left-hand side, your integral can be reduced to fiber-wise integrations. And the fiber-wise integrations are nice. If your sheaves are good, for instance, rank 1 sheaves, so on and so forth, fiber-wise moduli spaces are just Hilbert schemes on the fibers, and the invariance can be calculated. Partition functions of those things could have nice properties like modularity, etc., etc. So this is a threefold story. Let's go to fourfold. Example 2. I have fourfold now, X4, again, K3 fibered. I want to play the same game. My sheaves are still torsion sheaves supported on fiber. And this is just an example. So I'm not saying we are solving the problem only for this, but this is one of the nicest examples for the construction I'm about to talk about. Okay, again, example is I have torsion sheaves supported on finitely many K3 fibers of a K3 fibered fourfold over P2. I do the same game. Pull back, push forward. Now, actually, let me put this here. Now it's more complicated because support of G is codimension 2 in this fourfold. So if you pull back the push forward, you will see that you will get G. Again, you will get a split object. It's not a triangle anymore. But the cojoule resolution of the structure sheaf of the fiber actually tells you what you will get. You will get G back. You will get G tensor with conormal bundle, again of K3 in X4, shifted by 1, exactly like before, just you can compare it. You have this piece, exactly that thing, except now conormal bundle of K3 in the fourfold is a bundle of rank 2. Before it was rank 1, now it is a bundle of rank 2. Plus Koszul resolution tells you will get G tensor second wedge product of the conormal bundle shifted by 2. This is what you will get. And in fact, this conormal bundle is isomorphic to O of K3 plus O of K3. So this you will get G plus G shifted by 1, 2 of those things, plus G, well, second Chern product, second wedge product is just O, so G shifted by 2. Now you apply Arham FF again. If GG again, I'm sorry, what am I saying even? You apply this functor Arham blank G to both sides of this isomorphism. Okay. If you do that on the left, again, you will get Arham FF, which is our deformation obstruction complex, if you like, F dot. On the right hand side, you will get Arham GG plus, well, Arham. Remember that the shift in the derived category, when it comes out, it becomes a negative. So Arham GG with the -1, but 2 of them, because there are 2 pieces in here. And then plus Arham GG again with a -2. Okay, this is what it is. This is our previous complex G dot. And if you use Serre duality, you can actually see that this is our previous complex G dot dual. G's are supported on the fiber. Just use Serre duality. Look at Ham GG. Its Serre dual is X2 GG. That X2 is that shift by -2. And, you know, canonical bundle of the fiber is O. So there is nothing beyond that. So if this is G dot, the last term on the right is G dot dual. And in fact, this term in the middle, this is also self-dual. Self-dual via Serre duality is just self-dual. If you apply Serre duality to it, you will get it back. So this is what it is. Okay, so the right-hand side has some kind of nice structure, seems. Left-hand side, though, problematic. So it has homomorphisms. It has X1, it has X2, it has X3, and it has X4. I can look at the trace prefars, use the stability and say these pieces I don't care about, but as you can see, the cohomologies associated to the tangent complex of the moduli space, or the dual of the deformation obstruction complex of the moduli space, are more than 2. So this is non-perfect. So this implies that E dot defined as dual of F dot, the natural deformation obstruction complex is non-perfect of amplitude. This time it will not be -1 to 0, it will be -1 to 1. -1, 0, and 1. Okay, so that's that. But the reason I mentioned this example is that if you pay attention, one thing I can do is, oh, this thing, I need to move it around. So what is this thing? Okay. Let me use a different color. So look at this piece in the middle. So this is Arham GG shifted by -1 plus itself. GG shifted by -1. As I said, this term in the middle, which is now written in blue, is self-dual. So if you look at this Arham FF on the left-hand side, one issue is that it has 3 non-vanishing cohomologies, but as an object in the derived category, seems like it almost captures the same theory of the previous threefold that I gave you. The previous threefold had G dot plus D dot. This is exactly that D dot. So if you look at it, you will see that these 2 things are exactly dual to these 2 things. So in some sense, even though the left-hand side has 3 non-vanishing cohomologies, object and derived category that induces those cohomologies is kind of nice derived categorically. It's like twice the theory of the threefold. So F dot, we realize that F dot is G dot plus D dot plus G dot plus D dot dual. So if I just look at half of this thing, so, and we know that G dot plus D dot by our former construction induces well-defined invariance. It has a virtual class associated to it, so on and so forth. So what does that tell you? It tells you that you can take one of these pieces, let's call them L dot. So this L dot is getting mapped to, as you remember, this F dot was the derived tangent complex of the moduli space over X4 this time. And I can take this thing and I can basically take my derived categorically, I can take this guy and mod out by one of these pieces and take the other, get the other piece. So I can do this one, for instance. And that induces for me L dot, and L dot induces well-defined invariance. So in fact, I can define my invariance this way. If I see such nice splitting into 2 isotropic substructures of the derived tangent complex of half rank, I can take one piece and take the cone. This taking quotient means cone in the derived category. And then I hope that I'm left with L dot, which has a piece which induces well-defined invariance. So if you look at it, everything in here, L dot has half derived categorical rank as F dot. So you can really think of this derived categorically. This is similar to a Lagrangian. So in fact, this is what it is exactly. So the statement of the story I'm trying to tell you today is that in situations like Calabi-Yau fourfolds, where you have moduli spaces whose deformation obstruction complexes are ill behaving, they have more than required non-vanishing cohomologies. If you can show that globally over the moduli space is a derived Lagrangian foliation sitting, you can take quotient of the derived tangent complex of the moduli space by those Lagrangians, and on the leaf space you can define invariance. And those invariants are honest to God invariance associated to the original Calabi-Yau fourfold, because it's just the construction is still over the Calabi-Yau fourfold. Okay, so that's the story of today. So now I can switch a little bit to derived geometry. So in the sense of, as we said, in the sense of derived geometry, R Hom FF was the derived tangent space associated to moduli space, and alpha L dot dual to D dot of MF is going to be a Lagrangian distribution. Okay, so to make sense of this thing, not only I'm going to show you that modding out by this Lagrangian and working with this object is nice because you can define virtual classes and so on. In fact, I'm going to show you that whenever you have a derived moduli space and you have a Lagrangian distribution on it, globally defined everywhere, you can even say more about that moduli space. You can even say that maybe your moduli space can globally be defined as a critical locus of a Chern-Simons time functional. So even though we are in a Calabi-Yau fourfold situation, we have a still like threefold case, two ways of calculating invariance if we want to. Okay. So let us talk a little bit about these Lagrangian distributions then. So we are going to switch to, language of derived geometry over commutative differentially graded algebras to make everything rigorous. So first topic is, let me define for you integrable and Lagrangian distributions. Lagrangian distributions over DG moduli spaces, over differentially graded moduli spaces. Okay, so let us start with some A dot, be a differentiable, sorry, not differentiable, oops. I don't know what to do with this thing in here, okay. Differentially non-positively graded C algebra. So if we have that, then we can define, then let omega of A dot be the graded A dot module of Kähler differentials. Okay, so all right, so then from that, so what does this mean? Your A dot is not a commutative algebra anymore. It's a differentially graded commutative algebra, and it is non-positively graded. So A dot is similar to something like this. So it is A0 and then A-1, and it keeps going, and it's an infinity sequence, if you like. And over each piece here, you can construct your modules. You can construct your differential forms, the one forms, and then two forms, and you can keep going. Okay, so that's the, omega of A dot for us. So omega dot of A dot, in fact, this way can be constructed as a bi-graded mixed complex. So it's going to be sum over symmetric products of omega A dot, and I'm going to shift it by 1. Okay, this is a bi-graded complex. Why is it bi-graded? Because it has the degree which tells me which homological degree I am in. I can have an n form over A0 or an m form over A-1. So there is weight of the forms, which tells you which form I'm looking at. And then there is the degree of the forms, which tells me over which commutative algebra inside that DG algebra I'm constructing them. Okay, so that's a bi-graded complex. So now here is a definition: an integrable distribution on the spectrum of A dot. So if you like, this is what is the affine DG scheme, exactly like algebraic geometry. If you have the DG algebra, you can construct the affine DG scheme. So what is an integrable distribution? An integrable distribution is a data is given by the data of a pair. It's given as a pair. Okay, so what pair is that? This is what it is. So pair lambda dot comma dot and alpha, where alpha is a map from this bigraded complex, which I just, complex of scalar differentials over the CDGA, to some bigraded complex lambda. Okay, so this is a bigraded complex itself. And it's a bigraded mixed complex over C. That's it. Where alpha is a morphism. Alpha is a morphism of DG algebras such that it needs to satisfy certain conditions. Otherwise, it's not going to be integrable distribution. So such that these conditions are satisfied. First of all, this map from omega dot of A dot to lambda dot dot should be a weak equivalence, is a weak equivalence. Second of all, as a DG algebra, this bigraded complex itself needs to be written as symmetric end product of over lambda 0 dots of lambda 1 dots. Okay, so what does this say? It says that, so lambda 0, this is actually just the functions, 0 forms. And the first one is actually the weight. So this one is the weight, and this one is the degree. So it's actually telling you that this bigraded complex need to be generated by 1 forms. 1 forms over A0 and over A minus 1 and over A minus 2 all the way to the end. Okay. So in fact, because of this condition, you can see that omega dot of A dot itself is one of these guys. Certainly, scalar differentials are generated by 1 forms. Okay. Okay, so lambda 1 dot is needs to be a perfect DG A dot module. So this is the third condition. It needs to be satisfied, okay? So that's it. So let us look at this a little bit. So the story I'm trying to say is that this is the information of an integrable distribution. And I'm going to show you that Lagrangian distributions are a special case of integrable distribution. So we are going to see that Lagrangian distributions are special cases of integrable distributions. Okay, so in order to define Lagrangian distributions over the whole moduli stack, derived moduli stack, I need to study integrable distributions. Okay. Okay, so here's a remark. As I mentioned, we are working over a spectrum of A dot here. Where was it? Here, over DG affine schemes or affine DG schemes. Everything is defined over affine DG schemes. The remark is that you can do this over the derived scheme, derived DG schemes, but of course, you need to cover it by affine DG schemes and then show that integrable distributions glue. So this construction can be extended to DG schemes via gluing. Okay, so you need to glue it. Okay, which is actually the topic of my talk. So the story is, I'm going to show you that similar to the example of K3 fiber Calabi-Yau fourfold, moduli, the derived DG moduli stack of sheaves, which I just showed you, are going to be locally coverable by affine DG schemes on which you have these special case of integrable distributions. Those are the Lagrangian distributions. And as I go from patch to patch, in fact, altogether, these Lagrangian distributions constitute a sheaf of distributions, okay? And then I need to show you, in order to be able to define the moduli space as a critical locus or some suitable object from which I can calculate invariance, I need to show that this sheaf of Lagrangian distributions has global sections. This is basically what we are going to do, okay? So in order to define Lagrangian distributions, we need to define homotopically closed and symplectic differential forms. Okay, many people in this audience are familiar with the work of PTVV, but my experience is that it wouldn't hurt if I just give you a short review of those things. So given this bigraded mixed complex of Kähler differentials over our CDGA, which is over C, we have two differentials, as I mentioned. One of them changes the weight of the form. That tells you what form it is, one form, two form. So that is the derived differential. And the other differential tells you over which part of the CDGA we are, and that's the homological differential. So here degree of D dirham is -1, but its weight is 1. D dirham always increases 1 form to 2 form to 3 form, so on and so forth. Degree of delta is 0. If you have a n form on A0, delta shifts it to the n form on A -1, but it doesn't change the weight of the form. Okay, it doesn't change the degree of the form, sorry. Yeah, so weight of delta is 1. Okay, so that's what it is. I think I should write this actually backwards. Yeah, 0 and 1. Now, given this information, this bigraded complex with the two differentials, consider a parameter t to which we assign weight -1 and degree 2. Degree 2, okay? And this is something that PTVV defines. So the following construction of PTVV, Pantev, Vezzosi, Pantev, Toen, Vezzosi, Vecchi, and then Vezzosi. I don't know how to write it down anyway. I apologize. PTVV, we define for any k bigger than 0 and any n less than 0, the negative cyclic complex of weight n and degree k. So this is the negative cyclic complex of weight n and degree k. So what is it's associated to this bigraded complex of Kähler differentials over CDGA, and it is defined as a sum t to the j, omega j, j from 0 to infinite. It's an infinite series where each omega j is a k plus j form of degree n minus 2j. Okay, so for instance, For j equal to 0, it's a k form. It's a k form of degree n. So this is basically telling you that derived in derived geometry sense, because you're working over CVGAs, your forms are not just given by one form, but they are given a series of forms. Okay, and it is series of forms like this which define for you in the derived setting the notion of symplectic form. So in the derived setting, a symplectic form is not just one form, it's a series of forms. So when you set k equal to 2, for instance, you have this 0 piece, which is just a 2 form, but you have many other pieces in other degrees over a0, a-1, a-2. So it's a series of 2 forms, okay? So it is clear that the differential delta plus t times d dirham maps us from this negative cyclic complex of degree nk to negative cyclic complex of weight n plus 1 and degree k. Okay, because a degree of the delta is 0. Delta just changes the weight rather. Okay, so this way we can define, then we can define a DG C algebra, and that is going to be by adding over all weights, so all the forms together, I can just define this algebra of these forms, series of forms. Delta plus t d of dr. Okay, so this object here, I'm gonna put a big red cloud on it. This object is important. Why? Because the derived geometric notion of a symplectic form is a series that lives in here. And everything you know about symplectic forms is going to be extended to this notion in here. So let's define it. Okay, so definition. Let a dot be as above. A homotopically closed K form, think about 2 form, n form of degree n on affine DG scheme given by a spectrum of the commutative differential graded algebra is an element omega in this complex that I just defined. Okay, that is a co-cycle with respect to delta plus t d dirham. What does that mean? It means that before, for a form, symplectic form, for a form to be closed, we needed this condition to be satisfied. Here now we have that this conditions needs to be satisfied. T d dirham of W needs to be satisfied. But W is a series of W's over a0, a-1, a-2. So this is actually telling you that T d dirham of W0, it needs to be a co-cycle. So it's going to be minus delta of W1. So basically, and then T d dirham of W1 is minus delta of W2, and it keeps going like that. So up to homotopy, by W1, omega 0 is closed. And up to homotopy by W2, omega 1 is closed, and so on and so forth. So this is a homotopically closed form in the notion of derived geometry. Okay. So remark, by construction, any such homotopically closed form, omega is a series, and it has a free term omega 0. Sometimes this is called omega 1. You see, if you look at the notation, for instance, as soon as I fix the k to be 2, for instance, I'm looking at the series of two forms. And then this series of two forms is defined over A0 plus with a shift defined over A minus 1, A minus 2. That first term, which is defined over A0, that's the free term. And depending on the k, that's why normally sometimes they use this notation of bar, under bar notation to describe it. W bar is not derived closed, but it has to be a delta cocycle, as you saw. Okay, so why is this W0 important, or W bar important, when k is equal to 2 and we are looking at a series of two forms? The underlying free term of W defines an isomorphism from the tangent complex of the affine DG scheme to the cotangent complex, or cotangent sheaf, cotangent bundle, if you like. Okay, so the definition is let A dot be as above, an n-shifted symplectic form on a spectrum of the CDGA A dot is a homotopically closed, which I now defined for you. It's complicated, but anyway, two form W such that its underlying free term W bar, okay, defines a quasi-isomorphism from tangent complex of the affine scheme to, this is a weak equivalence to the cotangent complex of the affine scheme shifted by n. Okay, so now here is some of the remarks and results. So results that we know. PTVV in their famous paper showed that the stack of perfect complexes, M-perf, perfect complexes, has always a two-shifted symplectic structure. Meaning that when you realize this is stack as a derived DG stack, over it, you can have a form, homotopically closed derived form, whose underlying free term induces such quasi-isomorphism shift by 2. So shifted symplectic structure. So this is the first result. Second result is that not only that, for a Calabi-Yau manifold X, the complicated mapping stack maps from X to M-perf, maps from X to the category of perfect complexes. So basically, these are perfect complexes over X. This has a shifted, this has a 2 minus n, has a 2 minus n shifted symplectic structure, where n is equal to dimension of X. So if your X is a Calabi-Yau 3, you have -1 shifted symplectic structure. If your X is Calabi-Yau 4, you have -2 shifted symplectic structure. And this is for the moduli space of perfect complexes. Remember that this is way bigger than the moduli space I just mentioned an example of. Ours is a moduli space of sheaves, coherent sheaves, and it has a very much more geometric construction. It sits inside this moduli space of perfect complexes. Okay, so in fact, this is something that we needed to prove. So in a theorem, Borisov and Katzarkov. So earlier versions of this paper kind of were published 2 years ago, but it just recently got published. So I'm putting 2022. The most updated version is at least 2022, given X and P, a Hilbert polynomial with rational coefficients in variable T, a Hilbert polynomial, we actually constructed the derived quota stack of quotient sheaves on X with fixed Hilbert polynomial P. Why do we do that? Because these are the things that after modding out by automorphisms gives us a moduli space of sheaves. So we showed that this divided by GLM, where M can be determined by P, by the Hilbert polynomial P, has the following property, So the derived quota stack of sheaves with Hilbert polynomial P, quotient sheaves modeled by GLM, has a map to this mapping stack of perfect complexes on X. And this map is formally a tall map. So because this is the case, here we have 2 minus n shifted symplectic structure. Therefore, if I call this map I can take the omega in here and pull it back. So I upper star of omega, pull back omega, defines a 2 minus n shifted symplectic structure. On the quotient of the derived quota stack. Okay, so I have 1 minute. So maybe here I can ask, is it possible to have 5-6 minutes extra so that I can just mention some of the theorems about these Lagrangian distributions?
Yes, that's fine. Go ahead.
Okay, thank you so much. Okay, so this is the first statement that we proved. So as I said, this is our moduli space. Goal is, so we have some nice moduli space, and we have worked very hard to borrow the homotopically closed shifted symplectic form from the moduli space PTVV study from them and say that our moduli space also has shifted symplectic structure. Now, beyond that, in our moduli space, we have a Lagrangian distribution. And we would like to use that property to show that our moduli space is globally written as a derived critical locus of a function. Okay, so this is the goal. So let me mention the other theorem now. This is in the works, the 2 papers that we wrote after that original one. So this is Borisov and again Ludmil, myself, and Yau. So these are 2021 originally, but now both of them, the most updated versions of these things are now 2022 actually, because we updated. Given X, let us just focus on Calabi-Yau 4. Again, I'm fixing the Hilbert polynomial in with rational coefficients. So this is my Hill poly. Then there exists always GLM invariant Lagrangian distributions. Now I need to tell you on what. So let's call these Lagrangian distributions L dot. So L dots are going to be getting mapped to this derived quota stack that we constructed, mod GLM, and that thing was being mapped to the mapping stack of perfect complexes on the Calabi-Yau 4. Okay, so there is always such things, and the notion of derived Lagrangian distribution I defined. So now it is nice because I have the shifted symplectic form in here. I can pull it back to here, and I have the notion of shifted symplectic form in here. And now I can really treat L dot as a Lagrangian. So before, in the strict sense, if I have a symplectic form, a Lagrangian will be the one that omega vanishes on. Now, up to homotopy, omega needs to vanish on this L dot. Okay. So, okay. So let me make this more rigorous though. We take this omega, so we split I upper star of omega into real and imaginary pieces, imaginary parts. So in particular, so let's call them imaginary parts, real, and omega imaginary. Okay. And the statement is that we would like the Lagrangian distribution on this derived quota stack to be negative definite relative to omega real. Okay, a Lagrangian distribution with respect to omega imaginary part of this form is negative definite with respect to the real part of omega if the real part, so that is omega real, defines a negative definite two form on H1 of the Lagrangian distribution with respect to the co-boundary differential. Okay, so this is some kind of cohomological condition. If this is the case, then as I mentioned to you, this is what we are gonna do. We have the nice derived Lagrangian distribution. It gets mapped to the nice DG stack that we have. What am I gonna do? I'm gonna take this guy and mod it out by derived Lagrangian distribution. Just take the quotient. Okay, so let B dot be defined as derived quot x with the Hilbert polynomial, quotiented by L dot. So derived categorically, this associate cotangent complex of these things are just cone of each other. But then in sense of derived geometry, this notion of taking a quotient by derived distribution is defined by Getzgery and Nick Rosenblum in their book. Also, I think the first place we learned it from was the Tony Pantev just talked about it in the 2014 birthday conference of Maxim Kontsevich. But I didn't find any notes of Pantev constructing it, but it's actually in the work of Tony told us that it is over there and we found it. Anyway, so if this is this quotient, then we proved that this is the final part of my talk. We proved that B dot is a stacky quotient, stacky GLM quotient, okay? Stacky GLM quotient of a perfectly obstructed derived manifold, which is very, very important property. What does that mean? It means that there is a derived manifold C, derived manifold, okay, C, and on it, there is a bundle, a perfectly obstructed bundle, and then there is a section of it. And then B0 is the scheme structure of this guy in here. B0 is the derived zero locus of this section. And our B dot is actually this derived zero locus stacky quotient by GLM. Not only that, we also showed that, moreover, that the B dot, moreover, actually, wait, this implies that DG Quot XP mod GLM is itself is the derived critical locus of another section let's call it tau of the sheaf dual to this bundle, a perfectly obstructed bundle. So in fact, this itself is the derived critical locus of tau. Okay, so you have the derived manifold, you have an obstruction bundle on it. This is the derived version of the obstruction bundle. Your original moduli space is given by a GLM stacky quotient of the zero locus of section. That's the first statement. And then there's another section, tau, of the dual to this derived obstruction bundle. And the derived critical locus of that gives you the moduli space globally. Just turns out that sections of this dual bundle are functions that live in -1 piece of the underlying commutative differentially graded algebra. So these are -1 potentials, actually. These are not over the A0, but these are over A -1. So I think it is better for me to stop in here, but I can answer questions.
Can you go back to the definition of integrable distributions?
Integrable distributions.
The condition one, I don't understand.
Oh, this one.
Yeah.
Yeah.
Condition one is that it's of back equivalence. So there are two. There are homological differential and also the derived differential. By
yeah.
You mean with respect to the total differential or one of the?
With respect to, a good question, with respect to delta plus t times dr, yeah. With respect to delta plus d dirham.
Okay.
Yeah.
This condition is a little weird to me. If you consider zero distribution, then how do we expect it as equivalent?
If I consider
zero distribution.
Which distribution?
A zero.
I can't hear you.
Zero distribution.
Yeah, I can't hear you. Sorry. I'm listening to you.
So can you just explain why do we expect? What do you mean by this condition?
What do I mean? This is what it is. It's just a map. You see, just a map as a mixed graded algebras. That's it. For me, the distribution is just basically this information.
So the integral.
So these are complexes. These are bi-graded complexes. And then I would like to think of them as mixed DG algebras. So basically their differentials needs to satisfy Leibniz properties. And then the distribution, what makes it the distribution is basically these three conditions.
Yeah, so
is an integrable distribution.
in terms of the vector field, the distribution is defined in terms of the bracket. So here you take the view, consider the different.
Yes, actually, yes, you can also define it in terms of the brackets, yes. So this is actually equivalent to that. This is equivalent to that.
So you translate to this condition.
Yes. This is equivalent to that, but I need to basically write it down for you.
Yeah, I just want to ask for a trivial distribution, like constantly zero. That's
Oh, trivial distribution.
Yeah.
Well, trivial distribution trivially satisfies these three conditions, right?
Why it's a big equivalent?
Uh-huh. Well, that has to do with the maps. That has to do with the maps. Then we don't call it in that way, we don't call it a distribution, at least. We don't call it distribution that way.
Yeah, sure.
Yeah. I mean, that then forces some condition on lambda dot dot. I mean, that's kind of a trivial case. So.
Other questions? All right, well, thank you for your talk. Thank you, speakers.
Thank you so much.